Here is a ladder problem similar to what you would find on exam 5. So this is a problem that will deal with torque. A person is climbing a ladder leaning against a wall at a 70-degree angle, and they want you to determine how far the person can climb up the ladder before the ladder begins to slip. So it's this distance right here that we're after. So I have drawn a little piece of floor and a little piece of wall because those are important in terms of force. Equilibrium is the last point at which the ladder was stable. That's also the first point at which the ladder begins to slip. So in order to solve this problem, we're going to set net torque equal to 0 and force in the x and y directions both equal to 0. So you need an extended picture with torque to show where the forces are applied. But when you're thinking just about force, you would boil it all down to a single point of mass. And then you have these four forces. Normal up from the floor supporting the base of the ladder. The friction of the floor must be pulling to the right because otherwise the ladder base would slip to the left. There's the weight of the person downward because the problem tells us that the weight of the ladder is negligible. And we also have the force of the wall pushing left. That's the only reason the ladder could possibly be standing up. Notice where I have the force of the wall, the normal force of the wall pushing. I've got it drawn up here with a longer line. That's the line of action of the force, and that's going to help me when I get to torque. I also have my weight vector nice and long down here, so that's also a line of action for the gravitational force. So if I start off thinking just about force, and I require that the forces in the x direction are balanced, since there are only two, that means the frictional force must equal the normal force coming from the wall. In the vertical direction, since again there are only two forces and I'm requiring them to balance each other, the normal force is going to equal the weight. So now I need to go to torque. So I'm going to set up a seesaw problem. I'm going to pretend that this is a seesaw and the person's weight is trying to rotate the seesaw in the clockwise direction, and the push of the wall is trying to rotate the seesaw in the counterclockwise direction. So I'm going to set this up the way we always do with tau CCW for torque counterclockwise on the left and torque clockwise on the right. So this will be a radial distance vector to that normal push coming from the wall. And this will be the radial distance vector to the person crossed with the weight of the person. And I say crossed, of course, because we need to think about sine and cosine when we have torque. All right, so the radial distance vector for the wall is the entire length of the ladder. So I'll just put L in there. That might help you in case you have different numbers on different problems. And then the force of the wall I've already decided is equal to friction. So that's going to be mu mg. So that'll work for any size person, right? And then I need to figure out what I'm doing with angles. I need the radial distance from the pivot point to the line of action of the force. So that is straight up. The problem in this case gave me a 70-degree angle here. By alternate interior angles, there's a 70-degree angle here. So that means that radial distance up to the line of action of the force is opposite this 70-degree angle. So because it's opposite this 70-degree angle, I'm going to use the sine to get it. So this will be times the sine of the angle of the ladder. I don't really need to have the cross symbols anymore. Once I've multiplied times the sine, I'm now doing regular multiplication. For the radial distance of the person, that's the unknown I'm solving for. So, and then the weight of the person is just mg. And now I need to think, what is the perpendicular distance from the axis of rotation to the line of action of that force? And it's right here. It's the floor of the triangle. In other words, it's adjacent to this 70-degree angle. So this means I'm going to multiply times the cosine of my angle. So you can see I have it set up algebraically. And in many cases, that's easier than putting the numbers in too soon because you'll find you don't have to type in quite so many. So if I want to solve for D now, I'm going to take this left-hand side and I'm going to divide by mg. So you can see that's going to cancel out from both sides. And I'm going to divide by the cosine of theta. I think I feel a tangent coming on, even less to type in my calculator. So all I have now is the length of the full ladder times the coefficient of friction, which in class I often called the coefficient of stickiness, times the tangent of theta. And that's going to tell me how far that person can climb up the wall. I have a rather small person here. This person is only 22.5 kilograms. So it's about a third of my mass. So this person might be a child. And my particular ladder is 3.4 meters long. So I'm going to go 3.4 meters. The coefficient of friction I was given in the problem was 0.26, 0.26. And then my angle for the ladder was 70 degrees. And that will tell me how far the person can climb up the wall. So now I turn to my calculator and I go 3.4 times 0.26. Those of you who've been doing calculus recently, make sure you're in degrees because this problem is in degrees, times the tangent of 70. And I get my answer, which is that this child can go 2.4, and if we're quest crazy, 2.42877 meters up the ladder before the ladder begins to slip. So there's a ladder problem for you to practice torque skills. I do think OnRamps likes to offer those problems to you on tests. So good luck with that.